Good morning. I think we are waiting for a couple of more people to come. Let's wait 2 minutes till we start with the webinar. There are still people coming, so. So, good morning to all of you and welcome to our webinar, MEMS pressure die and sensor assembly. First of all, I want to introduce myself. My name is Klaus Rost and I'm the sales manager at Angst+Pfister Sensors and Power, and I'm your host today. I also want to introduce my colleague Janos Dusocki. He's our die specialist and he will guide you through the technical presentation today. He's also available to answer all of your questions during the webinar. Here you see both of us and also our contact data. If you have questions afterwards, you can ask us directly. Okay. Here the agenda for the webinar today. First of all, we want to give you a short introduction about Angst+Pfister Sensors and Power. Then we have 3 video sequences you can see here. The first one is a general introduction of pressure measurement, how a die works. Second one is then how a raw wafer will be produced. And finally, how the pressure die works in a sensor. In between the videos, we have 2 polls where we ask you some question and you can provide your feedback. We will also answer the question. They will come up during the videos, also at the end of each video sequence. For the polls, you see on the bottom right side, you see the 3 bar graphs with the polls. And you have to click then when we come to the polls, you have to click there and you can provide here your feedback. If you have questions during the presentations, you can click on the question button or also on the bottom right side and you can ask some question. I see that first some question already arrived. We will answer them also during the videos or between the video sequences, and also at the end we have a Q&A part. Yeah. Okay. Let's move into what Angst+Pfister Sensor and Power is. You can see here the different segments we are working in. Angst+Pfister Sensors and Power is in general a manufacturer of sensor and power components. Partially, we have also partners. They produce the components for us. You see, we are separated into 4 sub-segments. Let's start with the green one. It's power and drives. There we have motors and motor controller. We have power supplies. We have DC converters. We have current sensors. And we have interface components as well as passive components like inductives we have there in our portfolio. Okay. Second segment is geometry. There we have components. They can measure rotation, inclination, acceleration, and position. The third segment is the gas segment. You see on the purple right upside. There we concentrate really on gas sensors for hydrogen and oxygen. And we have also humidity sensors here in our portfolio. Last but not least, the most important segment for you, it's the segment pressure, flow, and temperature. As the name says, we have here flow sensors, liquid level sensors, and temperature sensors. And one of our key components are pressure sensors. And the pressure dies we bought with the acquisition of Equity belong also to the pressure group. Yeah. So if you have requirements for any of these products, please feel free to contact us. We will show you at the end again our contact data. Yeah. Now we will start with the first sequence of the video to give you a first introduction about pressure measurement and how a die will work.
With that, let's dive into pressure sensing. First, a pressure difference needs to be converted into mechanical movement or deformation. In most cases, this is achieved through a diaphragm. The diaphragm deforms based on the difference in pressure on its front versus its backside. This deflection then needs to be converted into some sort of electrical property. This can be done in multiple ways, one of which is the capacitive principle. Here, the distance between the diaphragm and the reference electrode results in a capacitance corresponding to the diaphragm's position. The piezoelectrical principle employs piezo crystals. These crystals generate a voltage when force is applied to them. This makes them suitable for high-frequency applications as they accurately measure pressure changes. They are not really suited to measure static or quasi-static pressure. Not to be confused with the piezoelectric principle, lastly, today we will be looking into the piezoresistive principle. Piezoresistors change their resistance based on the force applied to them. Now, instead of continuously measuring the value of a single resistor, multiple piezoresistors can be arranged as a Wheatstone bridge. The piezoresistors are then arranged in such a way that 2 of them rise in value and 2 of them drop in value when force is applied to the diaphragm. Taking the picture here as an example, let's assume that all resistors are equal. Power is applied between A and C, and as a result, the voltage between B and D is 0. If R2 and R4 now rise, and R1 and R3 drop in resistance, there is a positive voltage between B and D. This allows us to accurately measure resistor changes on the MEMS die. I would also like to re-emphasize that piezoresistors change their value when any mechanical stress is applied, no matter the origin of this mechanical stress. We will come back to this point later.
Okay, this was the first part, the general introduction about pressure dies. Again, if you have questions during the videos, you can type them into the question area. And now we start with the first poll. please click on the bottom right side on polls. There you see the question we are asking, and please provide your feedback. We give you 2 minutes to go through the polls, and then we will start with the next video.
So, how are such piezoresistors and MEMS die as a whole manufactured? Most of the processes involved are the same as the semiconductor processes used for logic or CMOS semiconductors. Every single wafer goes through an extensive list of process steps, and all needs to happen in cleanroom environments as to minimize production deviations. In addition to the standard semiconductor processes, MEMS production also employs some special processes that are mostly focused to manufacture 3D structures as opposed to the stack of quasi-two-dimensional layers needed for CMOS production. For reference, on this slide you can see a picture of a diced MEMS pressure sensor wafer on the left. Each of these die is 1.6 by 1.6 millimeters. On the right, you can see an example of a semiconductor process line. These production lines are located in clean rooms with ISO 4 classification. Let's now look at photolithography in more detail, as it is one of the most important processes in MEMS production. In image 1, you can see the surface of a silicon wafer in blue. On its surface, a functional layer has already been applied. For example, this could be metal layer. This layer covers the whole wafer surface. On top of that functional layer, a layer of photoresist has been applied. Then the wafer is exposed through a mask. This step happens in lithography machines, in our case a machine from ASML, the market leader in this space. The photoresist that is being exposed to the light is weakened. The weakened photoresist is then stripped away. Then the wafer is etched with an etchant that attacks the functional layer but not the remaining photoresist. Lastly, the remaining photoresist is stripped away and only the structure functional layer remains. Such a structure can have a width of below 1 micrometer to give a sense of scale. That is also why the cleanliness requirements for lithography in particular is this high, as even a single speck of dust can completely change the geometry of the structure. Similar to structuring a functional layer, lithography can also be used to mask a wafer before ion implantation. This process is used, for example, to create the piezoresistors of our Wheatstone bridge. Back to pressure die in particular, there is primarily one etching step where really a lot of material is removed, which is the backside cavity etch. To get this cavity, two different processes can be chosen from. The well-established way is wet etching. Due to the crystalline structure of the silicon, this etch happens at a very specific 54.7 degree angle. The etch is then stopped on a time basis, leaving some variation in membrane thickness as well as a bit of an uneven backside of the membrane. As opposed to wet etching, we are using deep reactive ion etching, or DRIE for short. This allows us to use an etch stop in the wafer, which results in a much more consistent membrane tolerance. For higher pressure ranges, this is not that critical, as for instance a sub 1 micrometer variation on a 50 micrometer membrane is not that significant. But on a sub 10 micrometer membrane, such tolerances become an issue. And to be clear, the image here are for illustration. In reality, the membrane is much thinner compared to the overall wafer thickness. The orthogonal edge also allows us to manufacture a much smaller die from the same membrane size, which has a positive impact on cost. In addition, a miniaturized die enables applications previously impossible, especially in the medical space. Think implantable or in-body pressure monitoring. Miniaturization is key. A glass on the backside of the silicon die is widely used on MEMS pressure sensors. Such a glass is bonded onto the silicon wafer using an anodic process. First of all, a backside glass enables manufacturing an absolute pressure die. For this, the backside glass is bonded onto the wafer under vacuum conditions. This results in a membrane that permanently has a vacuum on its backside, which enables it to reference the measured pressure against zero. It is useful, for example, in barometric applications. Another advantage of a backside glass is a very simple die attach process. The glass decouples the silicon die from the substrate and prevents parasitic mechanical stress. The main disadvantage of glass is the fact that it is amorph. This means that the glass is not crystalline, but closer to a highly viscous fluid. It can change shape across months and years, and this itself can add parasitic mechanical stress to the silicon die. This can then in turn lead to a long-term drift. This effect is usually negligible for higher pressure sensor die, but for low pressure die, which are much more sensitive, this can quickly become critical. One of the reasons long-term drift is especially critical on low pressure die is the difficulty to reset the offset. With higher pressure sensors, it is enough to, for example, shut down the tool where the sensor is measuring some sort of process parameter. Even with the tool shut off, there is always some pressure difference of up to a few Pascal or even millibar, but this can be considered zero for higher pressure sensors. For low pressure sensors, however, this may equate to the entire measuring range. For example, with just two open tubes attached to a sensor with our die in, there is a clear pressure signal if the door of a room is being closed or opened. For this reason, in many applications, it is impossible to do a zero offset calibration, and therefore the drift has to be stable throughout the lifetime of the sensor system.
Okay, this was the second part. Now we have the second poll. Again, please click on the bottom right side and please answer the 3 questions we have here. We give you again approximately 2 minutes. Again, if you have questions from the videos, please feel free to ask them. Also, the question button on the bottom right side is available. Okay, we will continue with the third sequence, and this is probably for you the most interesting one. This is how the pressure die works in a sensor, and you can, or we can support you during the implementation of the pressure die into your sensors. So please listen to the next video we prepared.
After mentioning the die attach before, let's now have a closer look at it. The die attach describes the process of gluing the silicon die onto the substrate. The goal of the die attach for low pressure sensors is as much decoupling from any stresses not related to a pressure difference as possible. As I mentioned, the piezoresistors pick up any mechanical stress that is exerted on them. One of the main sources of such undesirable stress is temperature. when two materials with differing thermal expansion coefficients are connected, a change in temperature always induces some stress. Therefore, it is helpful to choose materials with thermal expansion coefficients that are as close as possible to the one of silicon. The most critical material in that regard is the substrate. For instance, ceramics is a very good substrate material. Attaching the die directly to a PCB or FR4 can also work well. However, it starts to get really challenging when the die should be attached directly to a metal substrate, such as stainless steel. It should be considered that temperature effects can also be compensated to some degree at calibration. But the smaller the interfering signal, the easier it is to compensate for it. Another source of undesired mechanical stress is aging of materials. Across the lifetime of the sensor, different materials age in different ways, which across time can lead to an increasing stress in the die. To come back to the substrate materials, ceramic and metal are pretty different in terms of thermal expansion, but these materials only age minimally. FR4, on the other hand, is a bit less predictable, as across years it can change properties to a much more significant degree. This source of mechanical stress is really hard to compensate for. To isolate the negative effects of the substrate from the die itself as much as possible, the next thing to consider is the glue and the gluing process. The glue should be as soft as possible, which again helps to isolate the die from parasitic mechanical stresses. Of course, the glue needs to stay flexible across the lifetime of the sensor. If, for example, the glue becomes brittle after a few years, the positive effects of the glue deteriorate. To maximize the positive effect, the glue needs to have a sufficient thickness to ensure the die is far enough removed from the substrate. At the same time, the glue is not allowed to wick up the die walls, otherwise the decoupling effect is negated again. Lastly, the overall sensor package also has an effect on the die, though to a much lesser degree. As always, all these parameters contain some performance versus cost trade-offs. But overall, for low pressure die in the sub 20 kPa range, we advise against attaching directly to metal, and we consider a soft glue a requirement to achieve good performance. Let's now have a look at our specific die. They are manufactured using the latest technology, including DRIE and stealth dicing. This allows a minimal footprint at an exceptional SNR. At the same time, our die have an exceptional long-term stability, which is critical in many applications, especially in HVAC. Combined, this makes our die the best in class for low and ultra-low pressure sensing. I also want to emphasize we have an entirely European supply chain, from raw silicon wafer to final visual inspection. This isolates us from any ideas Trump might have on how international trade works. We also make sure to always have stock of all our product, not only for samples, but also for series production. This allows a much more flexible inventory for our customers. Lastly, we are eager to support you during design-in. A lot of know-how, not only on the MEMS die, but also on how to build the best sensor, be it material choices, die attach process, calibration, and so on. I hope I was able to give you some insight on MEMS pressure die, how it is made, considerations when designing a die, and what to pay attention to when building a sensor.
Okay, thanks for listening to the videos. As I mentioned, we ask you to provide also questions. So far, we got only one, and the question was, after all, do we get hands out? We will publish the complete webinar on a video on our website. You will find it there. So you can listen it also afterwards, the completed video sequence, and you can also store it on your computer if you feel it interesting. Yeah. There's another question. How many dies do you produce yearly? Janusz, probably you can answer this question.
Of course. Thank you. This depends really on the pressure range, as this is also really affected by the size, or the pressure range is affecting the die of the size, and therefore how many die are on a single wafer. But overall, we are manufacturing over 1 million die per year.
Okay. Next question. Are the dies manufactured completely in-house?
Good question. We ourselves do not have a MEMS foundry. Instead, we're working with a dedicated MEMS specialized foundry who's doing the wafer processing, and dicing is also done externally at a specialist, which we're working with. But as I mentioned, all these partners are located in Europe.
Okay. The next question is, what is the biggest challenge for low pressure dies?
So in terms of performance that they should achieve, one really critical thing that was also mentioned is the drift. Of course, at the same time, you need to have the sensitivity that is required for the application, but the sensitivity is much more binary. Is it good enough or not? While the drift is always there and can always be better. So I would point to this as the most challenging thing on the die level. When building a sensor, this is also critical, but on the sensor side of things, maybe the calibration is one of the critical parts, which is really in contrast with the cost involved for calibration. So there, it's really important to understand well the die and the whole sensor build-up to optimize cost versus performance at calibration.
Okay. Next question is, what is the dimension of your low pressure differential pressure sensor you can manufacture? Can you achieve something with a thickness of 2 millimeter maximum?
I assume that refers to the overall sensor. I would say 2 millimeter sounds really challenging. To give a reference, the die itself is 0.4 millimeters thick, and realistically, to sensibly employ a differential pressure sensor somewhere, you need some sort of interface to the pressure media, which usually is a port. So that would add some thickness, but in a very specialized environment, such as the implants in medical space or something like this, there are substrates thin enough with the die on top of it, where the overall buildup would be below 2 millimeters. So we really should look into this specific application.
Okay. Next question is, what are the difference of competition dies? So what makes us different from the others?
So one critical difference is this overall die size, which is to some degree dictated by the DRI technology versus the wet etching technology, which allows us to make the die smaller. We also cover a big range of pressures with a single layout, which allows much streamlined production at sensor production. And then, I mean, we just have a very high sensitivity and at the same time an exceptional long-term drift performance. So that really sets us apart from many competitors.
Okay. And I want to add, we are very cost competitive.
Absolutely.
Yeah. Okay. there are two questions. They are more or less a little bit the same. Which foundry company do you use for MEMS fabrication? Or the other question was, who is the manufacturing partner for the dies?
That's something we aren't open to disclose without an NDA, but as I mentioned, they are European.
Okay, so if you are interested in detail, we have to fix an NDA with your company and with Angst+Pfister Sensors and Power, and then we can disclose it. Okay. The next question is, what are the typical applications our sensors are used in?
So one of the typical applications is HVAC. In buildings where climate control channels are being monitored, the sensor die or our sensor die can mainly, there are two examples how they are used. So one of them is the flow of the air in the air ducts can be measured using the differential pressure. So you have some sort of orifice, some sort of limiting thing in the air channel, and by measuring the pressure difference before and after that, you can then calculate the flow. And this allows much more accurate control of the whole climate control of a building. The other thing in the HVAC space is monitoring filters. For example, you can measure the pressure difference before and after a filter, and over time the filter gets dirtier, and this will be visible on the pressure signal as an increased pressure difference. So this allows you to see how, if a filter needs to be changed, for example. Another really big application is medical, specifically ventilators, where it's really important to accurately control the active, like when air is pumped into the lungs of a patient, it's really critical that whenever a patient is pushing back because he is trying to exhale, that you're immediately shutting off the air pressure, and this can be measured with really sensitive low pressure sensors to avoid the patient feeling like he's being suffocated.
Okay, thanks, Janusz. The final question we have so far is, do you also have MEMS for automotive applications up to 150 degrees C available?
So 150 degrees C is perfectly possible on our die. We're also open to look into automotive applications in that regard. The more critical or limiting factor will be the other components of the sensor, specifically the die attach and the housing. That also needs to be able to withstand 150 degrees Celsius, but this we should look into specifically in terms of the application you're talking about.
But to make it clear, the MEMS die is capable for 150 degrees.
Yes, absolutely.
Okay, so it seems that there are no additional questions, so I want to thank you for your time and your participation, and I hope you found this webinar interesting. Again, we will publish it on our website, so you can always have a look on it if you want. I also don't want to miss the opportunity to invite you to the upcoming fair in Nuremberg, the Sensor and Test Fair. It's from the 6th till the 8th of May. We have a booth there. We are in Hall 1, booth 361. So feel free to visit us there and discuss with us in more detail. Janos and myself will be there. So if you have additional questions, feel free to come. And you will get from our website free entrance tickets if you want. Okay. So finally, again, I want to thank you and looking forward to get more questions and requests from you for the pressure dice. So thank you and goodbye.
Same from my side. Thank you very much for your time.